Welcome back to Stage 1 Mathematics Growth and Decay. In this video we're going to have a look at something called a logarithm. Now recall back to a few videos ago we were dealing with some exponential equations and trying to solve them. And for C and D it was simply a matter of factorizing and then matching the form. But down in E we had 5x to the power or 5 to the power of x equals 10. Now using our traditional methods of dealing with this sort of equation, we'd first try to factorize 10 and then we'd see if we can get it in the form of 5 to the power of something. But notice in this particular case it's not possible. So this is where we add a new tool to our mathematics toolbox called the logarithm. So what we can say is that for every exponential statement, there is an equivalent logarithmic statement. So jumping into some examples, for an exponential statement, we might see something of the likes of 2 to the power of 3 is equal to 8. Then we might have 4 to the power of 5. That would be equal to 1024. And then we could have something like 2 to the power of, or 10 to the power of 2, and that would be equal to 100. Now, if I use a different colored pen for the next little section, if we want to explain this in terms of a logarithm, we could say that 2 to the power of 3 equals 8. Well, that can be written in a logarithmic statement as log base 2 of 8 is equal to 3. So notice the match of numbers here. So this 2 over here is now the base of our logarithm. This power or exponent or indice is now the result of the logarithm. And finally, the right-hand side of this equation for the exponential is actually what's been applied or what's been used as a log 2. So notice the difference and similarities between exponential statements and logarithmic statements. Now if we do a similar application to this exponential down below, 4 to the power of 5 equals 1024, the equivalent statement is going to be log base 4 of 1024 or 1024 equals 5. And then similarly we can say log base 10 of 100 is equal to 2. Or another way of writing this is simply log 100 equals 2. So notice that I've dropped this base 10, and when we simply write log, it's implied that it's to a base of 10. Now if we look at the alternate exponential statement, we could say something of the likes of 2 to the power of something equals 8. Now if I grab my purple pen again, I can write 2 to the power of log base 2 of 8, because we know that this statement here is the same as this one here. So doing the same to the ones on or below, we can say 4 to the power of something equals 1024, and we know that the power in this instance is going to be log 4 of 1024, because that's going to equal 5. And similarly we can go log or 10 to the power of log 10 100 is equal to 100. Or if we want to write it in a more succinct manner, we can go 10 to the power of log 100, because the base 10 is implied when we leave out the 10. So it will be 10 to the power of log 100 equals 100. So in general, a to the power of x equals b, and x equals log a b are equivalent. They are equivalent statements. And also, by definition, a logarithm is simply an index or power. Thus, the logarithm in base a of b is the power that a must be raised to in order to obtain b. Substituting 1 into 2 gives x equals log a of a to the power of x, or log base a of a to the x equals simply x, which is known as the inverse property. So we'll leave it there for this video, and in the next video we'll do some examples.